have a conclusion about it and a discussion afterwards. Let's come to the problem motivation. An LLM, behind there is a transformer. That's a machine learning architecture, which actually came out 2017 by Google with the paper "Attention is all you need." And the key idea is that, like as a first or point of view, like imagine this black box where you give in a sentence. All the sentence gonna be broken apart and processed, and afterwards, in an autoregressive manner, we're gonna output word after word, which should give a good answer. The first part of this transformer is called the prefill stage, and the last part is called the decoding stage. The transformer looks like this. The first stage is called input embedding, and afterwards, one of the main ideas, the self-attention. And after this, there just comes like a feed-forward network, for example, an MLP, where add normalization keeps the data stable, and afterwards comes the output section. The first stage is called input embedding. It's the process of converting words into numbers or into dense vectors, whereas, for example, if we have the words king or queen, they should give like similar vectors with similar numerical values because they have the same or like similar semantic meaning. And what this also does is include token embeddings and positional embeddings. What are positional embeddings? The positional encoding is kind of the process of keeping the word order or the context of the words inside the data itself. So we can put numbers on them, and afterwards we have the word order, like the kind of information about the sentence or the words inside the data rather than in the model. Then to the heart of the transformer, the decoder block, where the first part is the self-attention. And the attention layer is also a main idea of the transformer, where we compute the attention is the part where we compute the token or the importance of the token relative to each other's in a sentence. For example, we can have a look at this sentence. This image should, like, the brighter the word is, the more important it is. So, like, for example, like Riemann is white, signed is white, August 1992. And what is also really important is that, for example, in language translation, we have in the first sentence European economic, and in the second sentence, we have economic européenne. So we can't have a one-to-one translation because, for example, in French, we have to swap these two words. So what the attention layer also does is it allows a neural network to derive the context of a word inside a sentence. Example, only John ate the apple and John ate only the apple. Those two sentences have not the same meaning. Then for the rest, it's just like a normal feed-forward network where in between we compute or add the output of the attention layer to the next block, normalize it for data stability, feed it into a MLP, where each token is going to process independently. This is going to become important later. And afterwards, for the next stage, we're going to add normalize it again. Hence, the output embedding, the final vector is projected onto a vocabulary-sized vector. And it's often tied with the input embeddings. And afterwards, we can either apply it or we're going to apply it for a softmax function. Maybe when you can remember at the beginning or at the second slide, each word of the decoding stage had a probability distribution. This is because of the softmax function. And afterwards, we're going to perform a top case sampling such that we don't have always the same answers or the same sentences as answers. Rather than we can use synonyms and use words maybe with lower probability, but which have the same semantics. And afterwards, next token prediction, the process is going to repeat again. Okay, so we derive this picture. Now, what we ask ourselves, or what really benefits from this model, is it's really parallelizable. So the prefill stage, we can parallelize each token at once. The decoder itself is also parallelizable, but the decoding stage, as I said in the beginning, it's in an autoregressive manner because we need the first word to process the next word. So we have to compute it sequentially, but the decoder itself is still parallelizable. And the thing about LLMs is they're quite large. For example, GPT-3 has over 175 billion weights organized into roughly around 28,000 matrices. So we have a lot of data which we have to handle. And also what we saw is from this image, we can derive that with larger context size, the throughput saturates because the CPU or like the processing units are becoming a bottleneck. So we can conclude that it's rather memory bound than compute bound. And I think we saw at the paper Lincoln that the prefill stage is still rather compute bound, but we're going to have a look at this later. But generally, it's memory bound. The latency also increases with larger batch size, and the GPU utilization is quite low. For example, on the Llama 2 model with the batch size of 128, it's 21%. So as a summary, LLMs must handle large amounts of data. It's rather memory bound than compute bound. Throughput saturates at some point, and the latency increases with larger batch size. We have an underutilization of the GPU, but the model is parallelizable. Okay, since we got now the problem, let's have a look at send. Hence, what do we want to achieve? We at first saw that we need a high memory capacity, we need high memory bandwidth, and model parallelism. Hence, the question we ask ourselves is, can we design a GPU-free system that enables large language model inference with high memory bandwidth, scalable capacity, and low data movement latency? But before we dive deeper into that, we're going to motivate something called Compute Express Link, short CXL. CXL is is an open standard for high-speed, low-latency interconnect between CPUs, or for example, network cards, and it uses PCIe buses, but uses its own protocols, and it's supported by, for example, Intel or AMD. And the motivation behind CXL is efficient memory coherence, sharing memory with low latency, sharing memory efficiently, and scalability. So this everything like we kind of need. And hence what we ask ourselves is like, can we use CXL or kind of like use CXL and put it together such that we have like a bigger system which we can scale? And hence Sense is a CXL-enabled GPU-free system. It uses CXL for memory expansion, and it leverages the PIM and PNM architectures. And its goals are, as the paper in the beginning said, address LLM inference challenges and to optimize performance and cost. So as I said in the beginning, we have the host or CPU, and afterwards we have a CXL switch, which connects to multiple CXL devices. And this is a really broad view. So we're going to dive into a CXL device, how it looks. And yeah, it looks like this, quite complicated, but we're going to derive it together. At first, we have the CXL port. The CXL port is the interface to the host or like to the rest of the machine, in which the CXL device can, for example, communicate with the CPU. More detailed, it looks like this. We have a receive communication channel where afterwards it's going to be converted into flits. Flits are the smallest data units in the CXL. And afterwards, we have either local to remote, remote to local, or host to local messages. And it's going to go in each block where it belongs. And afterwards, perform an integrity check, and the data is getting distributed and sent back, and maybe can even perform error correction inside of it. And afterwards, we have the instruction buffer where from the CPU or the host, the instructions are being stored. The program counter iterates through them and executes them. the decoder decodes the purpose of the instruction. And afterwards, already there are PNM units, where there's logic specifically for LLM or transformer exercises. We have a shared buffer to communicate between the PIM units and the PNM units, and it can also be used as a scratchpad for the PIM units. The PIM units are coming afterwards. The inter-device communication controller to communicate between the different PIM devices. And afterwards, now memory arrays are coming. At first, we have the load and store units, which handle the data transfers between them. A PIM controller, which controls the PIM logic. And afterwards, the GDDR6 memory chips, where unlike DRAM, they have processing units inside. And the memory arrays are the load store units, PIM control, and the associated memory chip. For the communication or the inter-device data flow, we use these channels. For the intra-device data flow or the data flow within the device, those are the channels. And for the control flow where the instructions go, these are the channels. Okay, and now I mentioned high scalability. And the scalability part comes here, where we can multiply or like add as much memory arrays as we want, or like as physically possible. So this is the big picture. And now we're going to go through an example together of matrix multiplication. At first, the CPU sends the data and the needed instructions to the port, where afterwards the instructions are getting stored in the instruction buffer, and the data is getting distributed across the different memory arrays. The instruction dispatch happens in the instruction buffer, where the program counter iterates through them, and the decoder decodes them. And afterwards, the data is getting again distributed or calculated, processed in the different PIM devices. And then while it's processing this data, it's still distributing the data between them all, or between the PIM devices. And hence the GDDR6 memory chips perform the in-memory processing. They can send it afterwards to the shared buffer, where we can perform some more processing in the PNM units. We're going to have a detailed look at the PNM units later. And we can do some post-processing afterwards, for example, if you want to apply a softmax function. Then we can either write it back to the CPU, or we can leave it stored in the memory chips for further calculations. Okay, how does the PIM and PNM architecture look like? Let's have a look at the PIM channel, at the specific PIM channel. At first, we have a global buffer, which acts as a shared memory space that connects all processing units across all banks through a 256-bit bus. Afterwards, we have 4 bank groups, or each group contains 4 banks, and each bank has an associated processing unit, where each processing unit can perform local operations inside the memory. And the processing unit contains 16 MAC units, and as said, it can perform in-place computations. The PNM units are quite interesting. At first, we have a decoder, which again decodes the instructions. We have RISC-V cores, which if we need logic or functions which are not covered by the fixed function logic, we can compute them there. Afterwards, we have reduction trees and accumulators, and they can all process data in parallel. And we have also an exponent processor, which uses Taylor series to approximate exponentials. And the idea between the PNM units is that all these functions are really important for LLM inference. Then in the end, we have a shared buffer which stores the intermediate results from the units. Okay, in the beginning side, we also have parallelism. this architecture contains or has two kind of, it's called hybrid tensor pipeline parallel mapping. And it includes two kind of parallel models. The first one is tensor parallelism, where we can split or perform processing parallel on a tensor, a large array, and distribute it across multiple devices for the goal of parallel processing of large tensors. And afterwards, it also has pipeline parallelism, where we can partition the model into different stages, and each stage assigned to a different device, such that we can increase the throughput because we can process multiple inputs concurrently. We're going to have a really short look at the ISA because it's quite complicated, but really important. The main ideas are to minimize off-chip data movement, reduce latency, and to leverage parallelism through granularity. So the first are for nearbank processing units, and these are to compute directly inside, or like to compute inside the associated bank for each processing unit. For the PNM units, as we saw, we have the exponent, reduction, accumulation, and RISC-V operation. And for the inter-device communication flow, we have send, receive, and broadcast. What also send has is it has multicast. But multicast is under the hood. It uses the broadcast instruction, and each CXL port has additionally a device ID, such that we can put in the device IDs and don't have to broadcast it. And afterwards, for the communication between the shared buffer and DRAM banks, global buffer, shared buffer, and shared buffer to global buffer again. The bottom four aren't that important. It's just to show how really granular this ISA is. Okay. Compute Express Link has also some drawbacks, but the paper argues against them. For example, it uses the advantages of PIM and PNM through the hierarchical data structure. And through the CXL-based memory expansion, it can mitigate the memory loss because of the processing units. And it can enable efficient communication between the devices and fine granularity in the ISA to mitigate the bandwidth limitations of PNM. Okay. Now let's have a look at the evaluations, how this model performed. At first, the evaluation methodology, they use the hardware platforms, the NVIDIA A100 GPU as an industry standard baseline, and the AIM simulator to model the PIM architecture and to simulate nearbank PNM units and capture the behavior of the LLM inference. The AIM simulator is, by the way, open source. You can see the link below if you're interested. And for the benchmarks, they only use the Llama 2 7B model. And as the metrics, they computed the throughput, energy efficiency, and the total cost of owner short TCO. Okay, the performance speedup is 2.3 in total, or as a median or mean. And what's interesting here is that in the prefill stage, send is actually performing worse than a GPU. So we can really see that a GPU in the prefill stage is rather compute bound than memory bound. But in the other stages, it's way better. The latency also improved, as we can see here. And the throughput also increased, because the yellow one is the GPU, blue one is the send. And this maybe looks a bit confusing, but the throughput is on the x-axis and the query latency is on the y-axis. So that's why send is below GPU throughput. But so the send GPU has better throughput. And the latency is also better. For example, we can see it in the last part with 512 input. In the decoding stage or in the prefill, GPU performs better, but send is in the decoding stage way better. So latency improved by around 2.3 times and throughput improved by around 2.3 times. And the energy consumption is also better. They compared it again with the A100 GPUs, and they achieved a 2.9 times better energy usage. Yeah, and the average frequency is around 1410 megahertz. And I don't have a slide for the TCO because there was only text, but the TCO, or the total cost of owner, was 5.2 times better, or 5.2 times tokens per dollar. Okay, let's have a look at the strengths and weaknesses of the paper. The paper really addresses the memory bottlenecks of the of LLM, and it's really tailored to an architecture for the needs of such software. We have a GPU-free design, and hence, as I also said, we have lower TCO because GPUs are quite expensive. We have a scalable architecture with the CXL devices, and hence throughput and latency. And what it also does, it's not only specific for LLMs. They explicitly stated and did all the evaluations on LLM models, but the transformer architecture is also applied on other programming paradigms, or not paradigms, but on other ideas, for example, audio generation. Hence the weaknesses, the ISA is quite complex. We have memory limitations due to PIM, where the paper argues with scalability. And they also primarily use the Llama 2 models for evaluation. We've nowhere seen, like, for example, GPT-2. And it's also heavily tailored to CXL. I should just keep going.
And maybe hold on a second. I think I'll set it up.
Is this good? Yes. Okay. Okay, so for our conclusion, this paper challenges the GPU-centric paradigm, specifically in large language models. It pays attention to the problem of memory boundedness, and it provides a scalable system. Okay. Let's have a discussion together. The first question is, what are the trade-offs between using PIM versus GPUs and TPUs for LLM inference? At first, the benefits maybe. Yeah.
I guess it makes sense to use PIM for the memory-bound operations, like the default stage, and GPUs and TPUs for the compute-bound stage for the first one.
Yeah. Yeah, that's right. But like for the first part, you said, what's the main goal of using PIM? Maybe.
I mean, isn't it to accelerate the memory-bound stage in the LLM?
Yeah, it is, but it's also to reduce data movement. Okay. And in the evaluation, the benefit, we had, for example, we had more energy efficiency. And we also have a really deep kind of parallelism. Can you remember which? It would have been bank level parallelism. But yeah, the first one was right. We have reduced data movement, and it's crucial in working with LLMs. We have better energy efficiency, and through the bank level parallelism, we can also parallelize across the different devices, or like inside the device too. And what are maybe the disadvantages?
Introducing a new instruction set definitely would add complexity to running any models on it.
Yeah, that's right. Yeah, that's actually right. That's the answer I have to the next slide, but something different. Yeah.
If you use both GPUs and PIM, you have to transpose the matrix or modify the format it is in which it is stored, right?
Yeah, true. But I'm going a bit more higher level, like not as detailed. Wait, how can I ask this? For example, we derived that the LLM is memory bound and it uses a lot of data. Would this architecture also benefit like for other programs?
So I guess the GPUs and TPUs are more versatile and can perform, like are well suited to compute to do other computations, whereas this is kind of really mainly suited towards LM inference.
Yeah. Yeah, that's right. I was looking for data flow heavy. But yes, it's right. Like it only benefits for data flow heavy tasks. And as you said, the ISA increased the complexity, so we have to adjust it in all compilers and everywhere. Okay, how does the ISA balance programmability and hardware specialization? For example, where is the part of LLM tasks? Remember the architecture? There was a block which had specific LLM tasks. For example, the PNM units had explicitly like exponents and all these kind of operations for transformer tasks. And another question, could we maybe also use this architecture? Okay, maybe I said it already, but could we use this architecture for other models or other programs? Okay, maybe I answered it already. Yes, we could theoretically. Okay. Yeah, and the third benefit would have been programmability support because we have a fine-grained controller over the ISA. Okay, and how does the ISA take advantage of the bank level parallelism? Remember the PIM slide of a PIM channel. Like we said, at the last part at the bottom 4 of the ISA slide, I said that it's just like the important thing that it's quite granular. And in the ISA, we could access like each bank separately. Okay, the main idea is that the DRAM is organized into banks, as we saw in a PIM channel, and that we have hundreds of lightweight PUs instead of main or a few main cores. And it should improve the throughput. And through the ISA, we have a really granular architecture where we can access each bank. And so we have a better parallelization. Okay, and for the last question, what limitations might arise from relying on PNM? Is there something we lose when we use PNM? For example, we lose memory space. And we saw that, like, for example, 1410 megahertz is quite low. Why could it be? Couldn't we use a higher frequency? But it's not specific for the paper. It's a general PIM problem. Yeah.
So, like, You mentioned that the latencies might be a bit slower because you're relying on the
The
DRAM.
frequency.
The frequency has
Yeah.
to be slower in order to be at the same speed as the actual memory of it that you're using, no? The same speeds there, because like,
there are other
otherwise you'd have like a
constraints.
GPU in the caches, it'll be a bit quicker there. So if you're using like the DRAM memory and the processor memory nearby,
I'm actually not
latencies
sure
would be
about that.
slower.
Yeah.
Or faster, sorry.
No, it's a physical constraint I want to hear. But yeah, maybe that's true, but I can't say.
Just a guess.
Is it about the thermals? So
Yeah.
if you clock it very high, you
Yeah.
cannot sustain the power that is displayed.
True. Yeah, so we have thermal constraints because we have a lot of processing units nearby. Okay. And the last one was limited logic and limited memory capacity, as we said. And also really important, the interconnect bottlenecks, because CXL uses PCIe. And I think NVLink is way better or like quite better at the moment. And I think the main concern about CXL, or the main counterpoint against CXL, is PCIe, because PCIe is slower than more modern interconnects. So this was the presentation. I first want to thank Konstantinos for the consultation. And yeah, are there any questions? Okay, thank you very much.
Go straight to the second one and have a break between the second and third presentation.
Can you download it again?
Okay.
So I have to only upload.
You can wear this one. This works now, so.
Can you go to the end? If you just click on the text box.
Is this not the correct one?
Oh, I don't know because it's animations.
Oh, okay. Yes, yes.
Yeah.
Okay. What do you want me to highlight about your introduction? Of your interest, let's say.
Hardware architecture.
Hardware architecture.
For AI.
Right. Okay. Okay. You see any break? You're not taking a break. Break.
No, because I have free today.
Well, that's
so
okay. It's okay.
some time.
Okay, folks. So we have Tristan here as the second presenter for today's session. So Tristan is first year master student in ETH in the electrical engineering department, and his area of interest most generally work on the computer architecture for artificial intelligence, and many more. So he's going to present work which you might find interesting, how to execute AI task more efficiently. So I hope Tristan is going to give you much more, excite you more about this one. Tristan.
No, thank you. Yeah, so this paper is, like Will said, about a new hardware architecture to accelerate LLM inference, like the previous presentation. And it's about using a lookup table rather than doing the actual computation. It's a paper that was presented January of this year by Microsoft, NTU in Singapore, and the Chinese Academy of Sciences. So I will go over the summary, motivate the problem, discuss the hardware and software contributions, and then results, discussion, etc. Okay, so for the executive summary, so the too long didn't listen is, according to the authors, that the next step in AI inference accelerator design is to skip the actual computation, the multiply and accumulate, for instance, in favor of lookup in pre-computed lookup tables. And the problem is that they are trying to reduce the model size because, as we saw in the previous presentation, models are now in the hundreds and hundreds of billions of parameters. And they run into the issue that we can't quantize any further, but they provide a solution. There's two parts, hardware and software. For the hardware, they first present a way of compressing vectors into a smaller representation. And then for the software, they provide a tool to convert existing models more efficiently into this new lookup table-based model to retain more accuracy and do it faster than previous model converters. So slightly more details. For the hardware, there's two parts. First, how to represent a model, how to quantize the model using the centroids, we'll see that. And then how to look up in a pre-computed lookup table that replaces the weights that we're used to. And then for the ideas for model conversion, there's 3 steps. First, replace the operations, then freeze the weights and train the centroids. We'll see what that means, and then train the weights again. Okay, and then a spoiler for the results. We care about efficiency. They have 1.4 to 7x increase in power efficiency over other accelerators. And even more impressive, 1.5 to 141x increase in area efficiency, mainly because we don't have any compute, or not, we don't have many compute elements. Okay, so the context. So I think most people here are familiar with as we discussed in the previous presentation, the fact that if we increase model size, we increase the data set size, we increase the computational resources, we generally expect an improvement in model accuracy and intelligence. This is a quote from a recent blog by NVIDIA that discusses that. And then a bit more quantitatively, this is a research paper from OpenAI with they evaluate different parameters. On the x-axis, you can see the number of parameters for 2 training scenarios, trained from scratch and pre-trained on existing text. And we can see that, as mentioned, the loss decreases as the models get bigger. So because of that, models have gotten bigger and bigger, and we run into, well, we want to reduce the model size for power and cost, area, latency reasons. So the field has done a lot of work in quantization. On one extreme, we had at the beginning floating point 6432, and we now have papers that present the idea of binary weights, so just 1 bit. And obviously, we can't scale a number to less than 1 bit. So this is what the authors mean when they say that quantization has ceased scaling. This is just another research paper and accelerator that demonstrates how lower bit width for operations, like a 2x2 means you multiply 2 data that have each 2 bits. And you can see that the energy per inference in this case decreases significantly as you quantize the model. So as I said, quantization has ceased scaling, and they hope to provide a solution to that. So there's 2 core ideas. The first, as I mentioned, vector quantization, and then looking up in a lookup table. So what is vector quantization? Well, they use a very simple quantization scheme based on centroids, which means just using fewer data points to represent the initial data. So imagine you have a vector, you have data points, and here they're very conveniently clustered in 3 sections. This would be your vector. There's 10 elements here. And as you can imagine, we can summarize the data with only 3 points. These are the centroids. And if we then look at what this looks like in the vector, there's only 3 elements. If each element is, let's say, 8 bits, originally we had 80 bits, now we have 24 bits. And that's how the authors got a sub 1 bit quantization, just the ratio of the 2. So the elements are still normal integers, floating point, fixed point, etc., but there's just fewer elements. Okay, the second idea is the lookup table. So this, I think, should maybe be called a hash lookup table, but essentially you have 2 parts. The first is a quantized vector that you will compare with your input, and you will choose the most similar row and then look up the pre-computed vector. And that's it for your computation. You don't need any multiplier, anything. You just already have the pre-computed output, and that was computed during training. Okay, so now more details. The contributions, there's 2 or 3 parts. Hardware, it's the first accelerator that is based on lookup table. And for the software, so they didn't invent the idea of a lookup table model, but they provide a much better way to convert that is faster and higher accuracy. And then if you're reading the paper from an implementation point of view, they also provide a useful design space exploration framework to do hardware software co-design, but I won't talk about it for time reasons. So yeah, for the hardware, this is essentially a summary abstracted away of the hardware. There's 2 main parts, the CCM, centroid compute module, and the IMM in-memory matching. They communicate along with the external memory that holds the lookup table. They communicate with abstracted away interconnect, and the CCM is responsible for finding the index to use in the lookup table. The IMM is responsible for fetching the data and accumulating it and building the final matrix. So inside the CCM are CCUs, the centroid compute unit. And as I said, the goal of the CCM is to find the index to use. So it has the input data and then the hash for each row. And it can perform computation in parallel, of course, because the big matrices in the model are separated into sub-matrices. And then inside the CCU is a number of chained DPEs, distance processing elements. And their job essentially is, if you were to implement this in code, it would look like this very basic algorithm where they compute the distance between a given input vector and the vector in that row of the lookup table. And if they go through each DP, computes it for one given row, and it gets the input from the previous row. And if the similarity is higher or the distance is smaller, you update the index and update the similarity, pass it to the next row, and you go through the whole table. And at the end, you have the best index. And then inside each DPE, you have a very simple hardware, a block to compute the distance, and then just a little bit of logic to update the indices and the similarity. So in the paper, there's 3 options for similarity or distance computation. The main one that they use is L2, which is a familiar sum of distance squared. But they also discuss L1, which is a simpler, more crude, just sum of absolute distance. And then the simplest but most crude loss is Chebyshev, which is just the maximum difference of any element between the 2 vectors. And this is a figure from the paper that gives more detail inside the compute, inside the DPE. So yeah, as you can see, there's very little hardware, and that's why this accelerator has such a higher area efficiency. Okay, now for the second half of the hardware, this is simpler. The IMM in-memory matching, responsible for getting the data and building the final matrix. So it gets, as you can see with the FIFO there, it gets the indices from the CCM. This is the hardware. So it has in parallel to process partial sums. It has a number of partial sum lookup tables, which it fetches from main memory, indexes into them at the correct location. Yeah. And then to accumulate the data, it performs a simple element-wise addition, sort of similar to multiply and accumulate. Stores that in the scratchpad as it builds the different sub-matrices, and then it has a block to apply different element-wise activation and to optionally dequantize the data if you need to give it to another accelerator, or if you need for any reason to bring it back to a normal representation. So this is the complete architecture. And then once you have the final result, it goes back in the CCM to compute the next layer, and so on and so on. This is, of course, all pipelined for maximum utilization. And so what's new? Well, again, it's the first lookup table-based architecture. You only need cheap adders or maybe shifters, no fancy floating point multipliers. That takes a lot of area and power. And they also claim that this is compatible with an in-memory approach, which, as we've discussed many times in this course, reduces data movement, et cetera, et cetera. Okay, software. So they provide a model converter called LUT-Boost, Lookup Table Boost. And this converter has 3 steps. First, you just simply replace the operators from a matrix multiply to a lookup. Then you freeze the existing weights while you train the centroids, and the centroids, as a reminder, is the hash in the lookup table that you use to index into the lookup table. And then you unfreeze all the weights and let it train again towards higher accuracy. So this one is very simple. You just replace the multiplications with lookup tables, but this gives a very, very significant reduction in the footprint of the model. And this is what they wanted to achieve. In this case, it's on the CNN ResNet 18, they have a roughly 20x decrease in model size. So they reached that goal. And then the second step, this is novel in this model converter. So the idea is to freeze the existing weights, which are already trained because this is an existing model, and then only train the centroids. The issue that previous converters had is that they did not freeze the weights. So the weights got untrained by trying to fit to the centroids, which were initialized randomly. And so because of that, it converged very slowly, and it resulted in a pretty low accuracy when you compare it to the baseline. Now, one challenge is that the L1 and Chebyshev losses are non-differentiable. And as we know from, I'm sure everyone here knows that to train an AI model, you need backpropagation. For backpropagation, you need to know the derivative of the operations to update the weights from the loss. Now, if they're not differentiable, that poses a problem. So what do you do? They take a very simple approach using a straight through operator, which essentially in the forward pass is just the function as normal, but in a backward pass, you just estimate the derivative as a constant. That's it. And they don't give any more detail, but with that, they managed to train the network. Okay, and then the final step is once you have roughly well-trained centroids, the initial weights, you let them train together to converge to a better accuracy. And this is all the steps. The key insight is to break down the training into 2 steps to avoid overfitting to poor centroids, which would be initialized randomly. And compared to previous approaches, converges faster and has a lower accuracy drop. So quantitatively, this is, I think on ResNet 20, so a CNN, the 2 steps you can see there. In orange, it's their work. So as you can see, it converges much faster and to a much lower loss in this case. And on ResNet 20, they managed to lower the loss by about, to lower the accuracy decrease by about 6% compared to previous lookup table-based converters. Okay, so now for the results, we care about power and area efficiency and then accuracy drop. So yes, what do we care about? Power efficiency, like I said, area efficiency, accuracy, and we would care about latency, but this is not discussed in this paper. And what do we want to compare against? We want to compare against previous accelerators that are more traditional, that perform an actual matrix multiply. We want to compare with other model converters, and we want to compare with just a baseline traditional model. Okay, so this is for power and area. There's a lot of numbers, but essentially we compare to pretty major, let's say, accelerator from the previous years. And we care about these 2 columns, efficiency. Now they have 759 gigaops per square millimeter, which doesn't mean anything, but what we care about is the fact that it's 1.5x higher than the next highest of the different accelerators, which is a good gain. And then a 5.6 gigaops per milliwatt power efficiency, which is 2x more than the next highest. Then for accuracy, so here we need to look at the orange and gray. Orange is their loss after conversion with L1 difference, and L2 is in gray, and they compare it to baseline. And then PCAN and PQA are previous ways of converting a model to a lookup table-based model. So yeah, this is just a reminder of the losses. And there's 3 observations that we can make. First, that using LUT boost, we only drop 0.75% accuracy compared to the non-lookup table baseline, which is pretty acceptable. Second observation, yes, we drop about 6% less than the previous converters. And the third observation is that with L1, we drop 0.84%, which is pretty similar to L2, which is a good thing because L1 is simpler to do in hardware. This was for CNN. Now for transformers, which as we discussed previously is kind of the most important architecture now. They compared with a model that has 125 million parameters. And yes, essentially we can see here they compared L1, L2, and baseline. They compared on distal BERT, which is a small version of BERT, and then BERT. And in summary, we can see that the accuracy decrease for transformers is quite a bit higher than CNN, but it's around 2% compared to non-lookup table-based models. Okay, so takeaways. Well, we've demonstrated that model scaling can still, model quantization can still scale below 1 bit by quantizing the vectors with a representation based on their centroids. And they presented the first lookup table-based inference accelerator. They significantly improved the model conversion technique. And then if you're reading this from an implementation or comparison perspective, they provide a way to design your hardware and software based on like the vector length and the size of the lookup tables, etc. So the strengths and weaknesses. First with the strengths, it's the first one to actually accelerate this in hardware. And I like the fact that they considered the whole stack. So although inference is maybe what you can think of the highest part of the lifetime of a model, training, I think we've all seen the figures from modern LLMs where it costs tens and tens of millions of dollars to train. So they provided a way to avoid retraining from scratch, and also a way to lower cost for inference. And then just in terms of writing quality, I think it was pretty well explained. It progressed linearly. The figures were high quality, so it was pretty pleasing to read. Now for the weaknesses, the biggest weakness, in my opinion, is that there's no detail on how this scales, both in terms of the control overhead when you go from a transformer that has only 125 million parameters to the modern LLMs with hundreds and hundreds of billions. Yeah, there's no mention of how this scales in terms of the overhead, but also error propagation. As you go with deeper models and wider models, does the accuracy drop increase? This is not discussed. I did contact the authors and they think it's not an issue, but we need data on that. There's also no discussion on latency. This, I do agree that to make a good discussion on latency, you need a full system design, because this approach is only for inference and it's only for matrix multiplication. If you want to do softmax or layer norm, you still need another accelerator. So, and all this would be orthogonal to their approach. But I think they could still have compared the latency of doing a matrix multiplication. Then, as I mentioned, there's not much detail on reconstruction loss. And there's no detail on how this is a compute and memory approach, or what would be the challenges or the pros and cons of doing compute and memory versus doing a more distributed, but more traditional approach. So for the next steps, if we were to continue this research, I think it would be good to discuss what a lookup table friendly hardware, a training hardware is, because right now we still need traditional hardware to create the lookup tables. And as we said, it's very expensive. So maybe there's a way to accelerate that with hardware computation of the losses, for instance. And there's I think also it would be interesting to discuss how training a model from scratch for lookup table, how that would change things if this scales, if there's a bottleneck in training, if it's compatible with current hardware, etc. So yeah, that's it. Are there any questions for now before I go into the discussion? Right, discussion. So I have 3 questions. First one is, we talked about compressing a vector by representing it with its centroids. There are many other ways of compressing a vector. This is not a new idea. So what do you think could be other good ways of quantizing a vector?
So maybe one thing is reducing its dimension.
Yeah.
Like PCA, for example.
Yes. So PCA was coming. So there's previous papers that looked at just removing data points. If you have 2 data points that are very close together, maybe you can represent them with fewer. And then, as you said, PCA, principal component analysis, is a very common one. You could also share the weights between, you could sort of have a bank of template vectors and point the input to those vectors to share the weights, to share the data, fit a polynomial with some bounds. Yeah, there's many different ideas. And this could be a good way to pursue this lookup table-based model. Yes, what you need to consider when choosing a model compression would be training cost, would be the cost of computing the similarity, because that's kind of the most expensive part in the accelerator. You need to consider, of course, accuracy, degradation, and how much you can actually reduce the vector size. Okay, second question. So this hardware was targeted at vector or matrix multiplication, which is the most expensive part of inference, but we cannot do things like softmax with this. So what else do we need for a complete AI accelerator? Yes. Okay. So this would definitely be embedded in a heterogeneous system where you need something else, either a CPU or another accelerator. You need some memory to connect everything, a memory controller to connect everything. So this is definitely not enough to do a full matrix, full inference. And then the last question, it's more open-ended. So this was targeting AI inference acceleration through vector quantization and approximate computing. So if we want to consider what other field we can apply this to, what do we need to consider? So this could be outside of AI, just anything. What are the trade-offs that are implicit?
I think, like, for example, when the hash function yields the same result for 2 different inputs, I think in an AI model, it shouldn't be a problem, because we then afterwards we have another iteration until we have the best evaluation loss. And I think actually LUT Shazam uses it.
I'm not familiar.
Yeah, or yeah, or
yeah. Yes. So I think we can rephrase a little bit what you said. So anytime you need to compute with a constant, in this case, it was the weight for a given layer, but it could be any sort of filter convolution or any sort of just generic constant mapping function. That would be a good way to accelerate it. And then yeah, another key thing is you want an application that can tolerate error. So of course, AI is not precise. You don't require super high precision output, but you want an application that also doesn't require super high precision. And you want an application that won't chain the errors over and over again, because then the error could explode. So you want stable error propagation. And then the other thing we want to consider is that, so as I mentioned, this is only for inference, and the lookup tables are computed during training, well before. So we want an application that doesn't necessarily require the lookup table to be generated or regenerated online, and doesn't need them to be generated real time. Otherwise, this can't apply. So does anyone have examples of a field where this could help? All right. Yes, I was thinking of, for instance, weather, which is a lot of convolutions. We don't need super high accuracy. I mean, if it's 0.1 Celsius away from the theoretical value, it's fine. Or if we want super low signal processing, like in wearables, anything that is battery operated, where compute is very expensive, relatively expensive, then this, I think, could be a good way to use lookup table based models. And that's it. That's it. Yeah.
And take the sure. except for you.
Should it right? 30 minutes or is it fine if I go over time?
No. We shouldn't go over time because we should give everyone the same. What do you
No,
mean?
over time, like you're gonna have a second minutes, right? It was 20 minutes.
No, it's okay for the discussion to go overboard, but your presentation. No.
Can we leave? I mean, if we leave.
Yeah. Leave from one.
So from the presentation. The presentation, I'm not sure who it was. Yeah, someone use Google Slides. Oh,
No, I mean,
yeah, no, I get it.
Arshita, something. How do we stop the slide con the slow? We want the presentation.
How do we get the presentation?
Ah, you have to stop.
Yes.
I was
Okay.
trying to exit that and I put down here, then that's why. Because you were sharing the thing there. You were sharing the thing.
Yes.
That's why.
Yes.
Okay.
This is fine. Yes, that's it. Okay.
It's also possible to see. I mean, I have some notes, like in order to see it in the presenter view. I mean, at least on my machine, the presenter also has some
The
notes.
speaker
here.
notes.
Yeah, I mean, it's possible. If not,
What about pointer? It's not a Mac thing, right? It
no,
shouldn't
it
be a
also
Mac.
works on Mac. I tried it before, but I don't know. I mean, I tried on advanced Mac and I didn't touch anything, so he just entered in. Maybe.
That's something. No, it's can't change. I can do that, but I don't think that's the issue.
Maybe I'll say 6.5 years.
It's okay. So this should be the notes that show, right?
This.
Can we go to slideshow?
Yes.
And then here, presenter previous isn't
This is
okay.
the same.
Yeah, maybe. Yeah, maybe.
Why would that be? So his notes.
Like even yeah.
So his notes, right?
Yeah.
No. You want your notes? Yes, I think you're right. Probably not.
Maybe screen. Oh,
No.
oh no. Oh, that. And then
Here
and then
and
screen.
no,
Okay.
sub display. But yeah, let me see.
We did that.
Let me see.
Go to this thing.
It's not. Oh, yeah.
Okay. It's
Wait, what?
I found it. No,
It was just there. Yeah, that's what I was thinking. What if I slide?
Is it?
No, no, no. You need to share the other screen.
You will share the other screen. No, no, wait.
It was actually just going there.
Give me a second.
So just share screen.
Where's Zoom? Oh, sorry.
This back.
Share,
Share this.
desktop too. Right?
Desktop too, yes.
Okay. Here you go. Is it fine?
Yes.
Do you want it? You cannot see it entirely.
Yeah.
Smaller. Smaller.
Oh, yeah, you can go smaller. Yeah.
Like this is the max you can scroll. If you want. Okay. Okay. Cool.
Okay, so everyone, let's start with the last presentation. Vlad is going to present to us this paper Facil. And Vlad is a first-year master student in the CS department, and his interests are virtual memory and software hardware co-design.
Can you hear me? Okay. DRAM address mapping for SoC-PIM Cooperative. Now I'm going to introduce the executive way to work. First of all, demand for rapidly grows, which implies that memory-intensive operations on edge devices demand has also grown, and also PIM or the paradigm provides this high bandwidth for performing matrix vector multiplications, but is a challenging problem to integrate into current systems due to the different memory layouts with the current SoC processors. If we somehow manage to solve this problem, we may be able to overcome the memory wall that has been seen in the recent years of computing. There are some problems we have to cope with, such as the tight memory budgets on edge devices, because this way we have to use PIM both as a processor and as a memory storage unit, as well as the conflicting memory layouts between PIM and SoC that I already introduced. This will lead us to incur some relayout data costs and also some redundant data copies, which we want to solve. The goals are to enable relayout-free, low overhead cooperation between PIM and SoC during the LLM inference. We also want to devise this flexible DRAM address mapping to match the optimal layout for each compute unit. And lastly, we still want to preserve the application transparency. The overview of Facil goes like that. So they introduce this mapping selector, which is a custom memory allocator that chooses the optimal DRAM layout for each tensor. It also stores some custom metadata into the page table entries. It augments the memory controller to support multiple physical address to DRAM address mappings. And lastly, it keeps the modifications non-intrusive in terms of what we change to the hardware and operating system level by leveraging huge pages support. The key results revolve over this responsiveness main metric, which is time to first token. Facil manages to greatly benefit LLM inference on various tasks, such as short conversation and code auto-completion. And it demonstrates effectiveness on 4 different platforms using real-world data sets. In the end, Facil is going to increase the responsiveness, decrease the inference latency, all of this while keeping the memory usage constant. First, this is the outline of my talk, and I'm going to start with some background. The is about LLM architecture and inference, which was already introduced in the first paper in a way, but we are tackling it in a different way. So LLMs are consisting of multiple transformer decoder blocks, as you can see in the figure here. Basically, one decoder performs multiple linear operations, which can be either memory or compute intensive. And the LLM inference process is split into two phases. The first one is the prefill phase, where multiple and 4 in this figure are processed simultaneously in a single pass through matrix multiplications in order to spit out this output token, which is your in the figure. This step is compute bound and runs on the SoC. The next phase in the LLM inference process is the decode one, which is autoregressive by nature, meaning that the output token from the previous phase is going to become the input token in the next phase. This is going to be with one matrix vector multiplication per pass. This step is memory bound, and we aim to run this one on the processing in memory engine, and in general is the bottleneck of our systems. The other part of the background is some PIM terminology that is relevant in order to understand the paper. First of all, a chunk represents the basic compute unit for the processing units, and we aim to have the elements within a chunk to be contiguous in order to minimize the row buffer. The figure here we see 3 chunks: the white, gray, and black one. Each such chunk 128 bits. Also, a tile represents a collection of chunks that are processed across all channels and across all bands. This is tile 0 associated with the weight matrix. Such a tile represents a matrix row-wise concatenation of chunks, and by this in an all-bank manner fashion. Yes.
There's some static. I'm not sure.
Maybe I should move less. Okay. Is it better now? Mm-hmm. Thanks. Is it better now? Yes. Okay. So we are talking about this matrix row-wise concatenation that allows us to operate on multiple banks at the same time. In the figure, we see these 2 chunks, the white and black one. They distribute on 2 different banks, which allows us, due to the DRAM bank level parallelism, to operate on both of them at the same time. Also, the processing units access the same matrix column indexes, which makes it easier to broadcast the input vector. Here in this figure, we see that tile 0 is responsible for the first 128 columns of the weight matrix. And lastly, we want to fit an entire matrix row in a single bank. This will allow us to avoid the partial sum reductions. And in this figure, they managed to get the first weight matrix row fitting into bank 0. Okay. Next, I want to discuss about what motivated the authors to work on this problem and what research question they tackle. Basically, on-device LLM inference is a crucial task in modern age computing for at least 3 reasons. The first one is the benefits it may bring to the table. It can enable this low latency private and offline AI. It also is already adopted by mobile vendors. For example, Apple Intelligence already runs on our iPhones, and some modern LLMs like Llama from Meta is now running on HSOCs as well. But you may also wonder, why would we like to tackle such a problem with specialized hardware like PIM? And I think this is a valid question, and I'd like to demystify it. So remember the second phase in the LLM inference process, the decode phase. This is memory bound, and this basically bottlenecks the responsiveness of our system. As we can see in the figure here, in figure 2a, more than 90% of the execution time is spent on performing these linear operations, the matrix vector multiplications. Also, the high DRAM bank level parallelism allows us to, gives the opportunity to PIM to accelerate these matrix vector multiplications. And by tackling the problem using PIM, we may be able to solve the challenge we can see here. So basically, in this figure, we show that, they show that the compute utilization is less than 1%, whereas the memory bandwidth utilization is very, very large. So the problem statement in short is how to share LLM weights across PIM and SoC in an efficient manner. And they consider this a hard problem because the SoCs expect some type of layout, the contiguous layout, in order to perform the matrix multiplications, whereas PIM requires this bank-aligned chunked layout to perform the matrix vector multiplications. At the same time, both the SoC and PIM use the same weight matrix, leading to conflicting data mappings. There are already some existing solutions in the field which we are not quite satisfied with. The first one is weight duplication, which leads to automatically 2x memory consumption, and it's impractical, especially on edge devices. And the other one is on-demand relayout, which leads to a time to first token increase of 3x in practice. And this is a big problem because this metric basically tells us how the user perceives the latency and the performance of our systems. So the core problem here is how to enable this efficient layout-free data sharing between the PIM and the SoC for LLM weights. And now I'm going to discuss the overview and mechanics that we can find in Facil. Starting with the overview, Facil provides this flexible DRAM address mapping, which allows both the SoC and PIM to share these LLM weights without the relayout cost or asking the user to change any of its code. The key ideas are the following. In Facil, we are going to introduce these multiple physical address to DRAM address mappings while accessing the LLM weights, while storing the LLM weights in a single memory location, so addressing it with a single physical address. Also, the memory allocator is going to choose the best mapping at allocation time. And in the end, the user is going to access the data using the same virtual address, agnostic of the mapping that Facil does underneath his perspective, or abstracted away from the user. The impact of the paper is quite huge. It manages to get this 2.6x time to first token reduction by eliminating the relayout step between the first and the second phase of the phases of the LLM inference process. As I like to see Facil, it's kind of split into two layers. So basically, in the software layer, the authors introduce this PIM-alloc function call, where the user passes the dimensions of the matrix through the function call, which is then passed along through the mapping selector, which is going to tag each page table entry with an ID. And afterwards, the user is going to use the same virtual address to transparently access the matrix. Basically, the user just uses the virtual address, and then Facil, abstracted away from the user, is going to read the data in the correct matrix format. The other layer we want to change is the hardware layer. Basically, for the page table entries, besides the physical address that is already stored in the entries, we also want to store the map IDs, and we are going to do that in the unused bits of the PTEs. And also, the memory controller is going to be augmented to choose the optimal physical address to DRAM address mapping based on these IDs that we used before. This will allow us to support not only the SoC layout, but also the PIM layouts. So this makes Facil a write once, run everywhere schema, because now both the SoC and the PIM can read the same physical address without requiring any extra copies or relayouting the data. In terms of the implementation, it revolves around the following design goal: to accelerate the LLM inference step on edge devices in a resource-efficient way. There are some constraints Facil has to solve. So there are some constraints that Facil still has to fulfill because it targets edge devices. The first one is that we do not afford an external accelerator. Basically, our DIMMs have to be PIM-enabled, so they have to work both as compute and as storage. We also want to integrate within the SoCs, so we want to reuse the memory controller and augment it in a way to be able to implement Facil. And lastly, the memory controller only supports these conventional DRAM mappings, which I'm going to describe a bit later. So there are some key challenges that we have to tackle in Facil. There are two of them, and the first one is the PIM-friendly format data storage that we have to support. This is easier because we can solve it inherently using huge pages. So what we're going to do is we are going to use some huge pages of 2 megabytes in order to control the physical layout, and then we are going to leverage the unused bits in the page table entries, as we can see in the figure here, to enforce the chunked or tiled layout that PIM needs. It's important to note that we need the huge pages because this gives us more unused bits to work with, and we have to store the map ID in the unused bits. So if we were to use the conventional 4 kilobyte pages, this would, there wouldn't be enough unused bits to work with. The last challenge, the harder one, is the SoC to PIM efficient data sharing. And this is a hard problem because besides the fact that we want to be as non-intrusive as possible with our changes to hardware and operating system, we also must preserve this 1D array abstraction that is expected by all high-performance mathematical libraries like CoBLAS. Another key point about our implementation is that we want to do minimal hardware and software augmentation. We do it in 4 steps. At the user software level, we add this mapping selector, which chooses the optimal data layout that is, we add this mapping selector, which chooses the optimal layout based on the parameters that the user already passed to the PIM-alloc function call. The OS pager has to change by extending the mmap system call to take this map ID as a parameter and write it to the page table entries, as we can see in the figure here, in the after figure. Also, the page tables now do not store only the physical frame number, but also the map ID in the unused bits, as I said before. And lastly, the memory controller is going to be augmented with this MUX-based mapping selector, which is basically an N-to-1 multiplexer added per each DRAM field. In the picture here, I depict the multiplexer for the channel field, but there are also some other fields like rank, bank, row, and column, and together they form an array of length 5, an array of 5 N-to-1 multiplexers. The mapping decision in this multiplexer is decided based on the map ID value, which is wired as the select line in the multiplexer, as we can see highlighted in the figure. So with these design decisions in mind, we managed to get Facil working on the existing SoC memory controller after augmenting it. We require no additional memory layout. We require no additional memory to track the metadata. And in the end, Facil manages to achieve this seamless SoC to PIM cooperation at zero copy inference cost. So let's discuss about the main results and some key findings that I'd like you to take out of each figure I'm going to show later. Starting with the evaluation setup and methodology, which is pretty straightforward. So they test on 4 devices: Jetson, Orin, MacBook Pro M3, Lenovo IdeaPad, and iPhone 15 Pro. Remember the first step in the LLM inference process, the prefill one, that was compute bound and does some matrix multiplications. These operations are going to be done on the GPUs for the first 3 devices and on the neural processing unit for the last device. Also, the PIM model under test is an AIM-style PIM, which is simulated in a simulator called DRAM sim, which features 2 ranks per channel, 16 banks per rank, and 2 kilobytes rows. And lastly, the evaluation metric again revolves over the responsiveness metric, the key one, which is the time to first token. They analyze the alpaca and real human eval data sets, on which they measure not only the time to first token, but also the time to last token by varying the prefill and decode token lengths. So in order to measure Facil's latency, they they perform the prefill phase, the first phase of LLM inference on the real hardware and measure it there. And then the decode phase, they offload it to the PIM simulator, perform the matrix vector multiplications there, obtain another timing, and then they sum up these 2 timings in order to obtain the Facil latency number. They introduce 2 baselines. The first one is the hybrid static baseline, which basically does matrix multiplications on the SoC and matrix vector multiplications on PIM. As you can see, this is a static strategy because it doesn't do any smart profiling in order to allow the implementer to take more informed decisions on when and where to offload different works to SoC or to PIM. Then they come up with this software-based optimization on top of hybrid static, which is hybrid dynamic, which basically does some runtime profiling to determine when to offload this prefill phase to PIM or when to continue running it on the SoC. And in order to provide an apple-to-apple comparison to this baseline, when they compare Facil against it, they also incur this relay out time in simulation for hybrid dynamic and sum it up to the hybrid dynamic latency as well. It's important to note that this baseline, the hybrid dynamic one, achieves non-negligible speedups on top of hybrid static, but Facil manages to beat both of them at high margin. Just to announce the results, Facil is going to be able to eliminate the relay out overheads, leading to better responsiveness. And I'd first like to start with the time to first token results, because this metric captures the user's experience with interactive applications. On the x-axis, we see the tested devices, and on the y-axis, we see the time to first token speedup, whereas the different color bars depict different prefill token lengths. So first of all, we achieved the following geomean speedups: 289x for Jetson, 219x for MacBook Pro, 155x for IdeaPad, and 236x for iPhone. And what's important to note here is that the time to first token speedup is inversely proportional to the prefill length. What I mean by that is that the longer the prefill stage takes, the more the relay out cost gets amortized, and the time to first token speedup provided by Facil is going to decrease. The main takeaway here is that Facil manages to reduce this metric, the time to first token one, by eliminating the relay out costs, as I said before. The other takeaway is that short prefill length applications benefit the most out of Facil, and there are plenty of use cases of such applications. For example, chatbots, which are latency sensitive and interactive by nature. We can also see in the figure here that for prefill length of 8, each device achieves the highest TTFT speedup compared to other prefill lengths when we consider a single device, for example, for Jetson. And the last key takeaway for this metric is that this metric speedup is greatly influenced by the arithmetic intensity of the device's reach point in the roofline model. I assume you are familiar with the roofline model. So the idea is that the lower the arithmetic intensity, the faster the TTFT speedup diminishes. And this can be easily seen here in the paper. They report that the MacBook Pro and iPhone, both of them have low arithmetic intensities. This is why you see this steep curve in the TTFT speedup diminishing compared to Jetson and IdeaPad, which is more lenient, let's say. We should also touch on the time to last token metric, because this is a more comprehensive one in the sense that it covers the latency of both LLM inference phases, both prefill and decode. On the x-axis, we see the decode token length, and on the y-axis, the prefill length. And in each cell of the heat map plot, we depict the TTLT speedup achieved for a given prefill and decode combination. So for short decode phases, we managed to achieve great speedups. So for D less than 64, we achieve speedups of more than 10%. In this extreme case here, for D equals 8 for the NVIDIA Jetson device, they achieve speedups of around 70%. While on the other extreme, for long decode phases, for example, D equals 128 on the Lenovo IdeaPad device, they achieve negligible speedups of around 3% with Facil. The main takeaway here is that Facil manages to reduce the time to last token metric by performing faster prefill phases because it avoids this relayout cost, and it also performs faster recode phases by offloading specific tasks to the PIM accelerator. Lastly, devices that exhibit low memory bandwidth utilization benefit the least out of Facil. In the paper, they report that the Lenovo IdeaPad device achieves a 33% memory bandwidth utilization, which is very low, and this is why it gets the lowest gain out of all the 4 devices that are being tested in the paper. Let's discuss about some conclusion I'd like you to take out of this talk. So first of all, reiterating over the challenge, so in the paper, they want to solve this problem of sharing LLM weights efficiently on edge devices between PIM and SoC. And they report that it's a hard problem, remember, because both the PIM and the SoC have conflicting memory layouts. The main contribution in the paper is that they come up with this flexible DRAM mapping for cooperative SoC-PIM LLM inference, while removing the relayout cost completely, requiring no LLM weights duplication, all of this while still keeping the programmer transparency, meaning that there's no code that has to change at the user level side. Also, why this matters is because Facil manages to solve a real-world problem, the on-device LLM inference problem targeted on edge devices, with minimal hardware and software modifications, which makes it practical for edge SoCs. And lastly, it manages to do this by increasing the responsiveness because it reduced mainly the latency of the memory-bound step of the LLM inference process, which was the second one, the decode step. There are some strengths and weaknesses I'd like to talk about from the paper. The first one is the novel insight and perspective. So I really like that they address this efficient SoC to PIM data sharing challenge, which was not addressed before, and they solve it in the context of resource-constrained devices. Also, the programmer transparent approach is also a plus because they require no code changes and preserve the programmer abstraction, which automatically, I assume it makes it more, this proposal more likely to be adopted in the industry. The virtual memory stack changes is also non-intrusive because remember that map ID that I talked about that is stored in the unused PTE bits. This means that we do not require any additional memory to track this kind of metadata. And such an approach is feasible because the maximum number of map IDs is at most 14, as reported in the paper. Otherwise, we wouldn't have been able to store all the map ID values in the PTE bits. On a similar note to the previous strength is the DRAM address mapping design, which is smart because it limits where the map IDs can be stored in the page table in the DRAM address. And in the paper, they also provide this theoretical analysis on the maximum number of map IDs, showing that only a small number of map IDs, which is 14, can exist. And this allows the implementer to minimize the modifications to both operating system and memory controller design. Lastly, the adoption feasibility is important because in the paper, they clearly state why it may be feasible to adopt Facil in real systems now. Through the following example, they show this mapping algorithm, which needs to retrieve information about the memory system, which is something we can already do in operating systems like Linux because they provide interfaces up to the user space to do that. Since no paper is perfect, there are also some weaknesses I'd like to highlight. The first one is that the evaluation assumes full memory bandwidth availability. This is a big problem because remember that we are targeting edge devices, and on edge devices, most likely there will be other non-Facil processes running concurrently in the system, consuming memory bandwidth as well. So I feel like this is too strong of an assumption. Also, they changed too many levels of the hardware and software stack, even though they say their changes are non-intrusive. And I'd say this is due to how they due to the implementation idea. Basically, they have to change this address mapping. They decide to change this address mapping schema, and this requires interaction across the stack, modifying both hardware and operating system, decreasing the chances of adoption again. So there's also this thing that they only target near bank PIM. So I'll say it targets a two specific PIM use case, arguing that this is the only PIM class that has seen commercial products by now. They also have this section about DRAM address mapping section in the paper, so section 4.b, which was a bit too short, lacked depth, and skipped relevant explanations. And this was an important section in order to understand the implementation details. The same goes for the key concepts like map ID. They are named very early in the paper, but they are only presented a bit, they are defined a bit too late. So the first time I read the paper, it was very hard to me to even understand what this map ID really even means. And in terms of the ML background, they provide some shallow background about LLMs, transformers, and ML workloads. However, it seems like the authors already assumed that the reader is familiar with this topic, which was not the case for me. And some nitpicks. So there is also this thing that they modified the new PIM simulator to extend the low-power DDR memory. However, they do not open source these changes, which makes it hard to reproduce the results, as well as they do not foster collaboration on top of the changes that they made in Facil, because you do not have the code to continue working over that. And the nitpicks come now. So there are some graphs which I thought they are unclear. For example, the colors here were hard for me to decode. For example, I couldn't really differentiate between these two colors. And then there were some English grammar mistakes in the paper. This was my presentation. If you have any questions, and if no, I'd like to start the discussion section. Okay, so I have 4 questions for you. The first one is about programmer transparency. So remember, the main strength of the paper was that they do this programmer transparent approach. They do this minimal hardware software modifications in terms of operating system and hardware, and they create this new PIM-alloc function call, which is exposed to the user, and everything then happens abstracted away from the user. So my point here is, I mean, this is more of an open question. I'm wondering, do you think this transparency to the programmer should be preserved? I took one side of the coin when I devised the answers, but I mean, I look forward to hear the other side as well. I mean, yeah, so like a hint, if you are going for yes, I think I would think about which kind of benefits are very important that we don't want to lose. Do we have lost them if we decided to break this programmer transparency? And if you want to go for no, then something like which kind of benefits you can get out of breaking this programmer transparency. Okay. Yeah.
So I guess if you argue yes, then because it's easier for programmers to basically adopt this.
Sorry, can you say again?
If you say yes, then because it's easier for the programmer to adopt this.
Yes, I think that was my main point. I also said yes, and that was the first thing. Do you have anything else?
If you say no, I mean, you could argue that shouldn't be always preserved, because there might be some specific use cases where you have some extra outside knowledge that allows you to make smarter decisions than they otherwise would be made automatically.
I think this also makes sense, and we're going to talk about it in a second, but I mean, yeah, keep that idea in mind. So first, yes, I mean, I also said that because due to the simplicity to the general user, basically the users do not have to think about these low-level mapping details, and it's easier for us, the implementer, to design an easy-to-use correctly interface, because if you abstract everything away, the interface is going to be simpler, of course. My other point was about compiler and expert flexibility. If you keep the transparency, the system's runtime and compiler heuristics will automatically decide whether the data is going to live in PIM-optimized or SoC-optimized memory, which will allow us, again, to reduce the API surface and continue working with the standard mmap APIs. And by standard mmap APIs, I still mean the ones I presented in Facil, where they basically extended it by adding this map ID parameter. But then for the follow-up question for question 1, I was... Yes, okay, yeah, my point is, what if we sacrifice transparency? So taking the other side of the coin, do you have any things on the cons? I mean, one of my points is also what you already said, but yeah, if you have anything else to discuss about. I mean, that was a pro. I also have some cons here about sacrificing transparency. Just like a hint, I don't think maybe about portability. What would be a problem if we sacrifice transparency? Okay, then maybe, yeah, I'll show you my first idea. So of course, the API complexity increases, right? Because the developers must learn and use new mapping calls, as well as we have to devise more complex interfaces. The question related to low portability is that the idea is that if you break this transparency, the code has to be more tailored to a PIM SoC combination, and this may not transfer clearly to other platforms. Remember, in the background, I showed those chunks layouts, and I showed those squares of size 8 × 128 bits. Those were HBM style PIMs. In the evaluation, they used another type of PIM, which is AIM style PIM. That one has a completely different chunk layout. Those are way shorter and wider. So basically, if you implement something on HBM style PIM and then you want to move it on an AIM style PIM, you have to modify all your function calls. And lastly, what Kuba said is that it's going to provide an error applicability. It's best suited for HPC deployments in my mind, because here maybe the extra control is justify the burden, but still remember that we target edge devices. And in that case, I doubt anyone is going to do HPC deployment. So it's up to you to decide if it's a strong point or not. For the second question I had was about interference between applications on edge devices. So remember that Facil modified the memory system to support these multiple mappings. And my question to you is, do you think this modification addition of mappings, could this cause interference or suboptimal mappings for other non-Facil processes running in parallel on the system? maybe as a hint, in the paper, they do not analyze this multi-process contention. But if you were to think about it, what can happen? I mean, if multiple processes run in the system, do you see any way they could interfere? And also, yeah, remember that we do not have a separate accelerator. So yeah, we kind of share the DIMMs. Any? Okay, if not, I'll continue. So I said yes, because I mean, the paper, as I told you, doesn't analyze multi-process contention, but my take on it is that we are running on edge systems which are tightly have tight memory budgets. So switching between these mappings or collocating different workloads may introduce cache pollution or put more pressure over the TLBs. My third question would be about quality of service challenges in Facil, and it's similar to the previous question. I'm thinking about the interference between PIM and non-PIM memory requests. Remember that we use the DIMMs both for the SoC and PIM processing. So definitely we are going to have some PIM requests being scheduled and some non-PIM requests. And our goal with Facil would be to make sure that, I mean, to minimize the impact of Facil on basic processes that are running on the SoC. Do you see any kind of solution to this problem, to the interference problem, the quality of service problem that I just stated? Or I don't know if you have any ideas. I think there are plenty of ideas you can tackle it. I have a pretty primitive idea, but if you have anything to add over it, okay. If not, maybe I can tell you about my idea. So I thought about some static bank partitioning, basically split the set of banks into two disjoint subsets, one for PIM and one for SoC. The PIM generated DRAM commands are going to go to the PIM banks, and the same for the SoC. There are some pros in this way. I mean, this way we could eliminate the row buffer thrashing between PIM and the SoC, because now the banks that they target with their DRAM commands are completely independent. And the other thing would be predictable latency isolation, both for the SoC and the PIM, because, for example, before we could have the SoC workloads get some unexpected page misses due to work that was offloaded to PIM and mapped to the same banks. But now, as we separated it, we don't get into this problem anymore. And some cons will be this may be considered to be infeasible to implement on edge devices, because we may not afford the extra hardware to implement this kind of bank partitioning scheme, as well as we are going to have the effective row buffer pool for each domain, which will lead to DRAM underutilization. If you do not have a workload which is partitioned which is balanced 50% memory request from the SoC and 50% memory request from the PIM. And my last discussion point would be about the real-world bandwidth contention. So remember the first weakness I showed in the paper about the evaluation. I said that the evaluation assumes full memory bandwidth availability on LLM inference. And I said that's too strong of an assumption. So let's think together what can happen when other processes share DRAM. I think this is like a straightforward to answer question. Against, I mean, it's complementary to the interference question. I mean, do you see any problem with, I don't know, energy, performance, any kind of metric? Okay, so I'll say that yes, definitely performance may degrade because now the bandwidth contention may stall both the matrix vector and both the matrix multiplications. There are some current work ideas in the field. Does anyone have an idea about any work of this? Also didn't know about it. Ataber told me about it. It's called async DIM in HPCA 2025, and it evaluates how to overlap host side work with near memory execution in order to mitigate this DRAM bandwidth contention problem that we are talking about. And there are some future work ideas I had in mind. The first one would be so-called quality of service aware mapping map ID assignment. Here I want it's like a high priority model, like an interactive chat, to be mapped to low contention banks. And then I'll have a dynamic remapping schema at runtime where I monitor per map ID bandwidth usage using some extra hardware counters. So basically, each time low priority map ID spikes in bandwidth memory bandwidth utilization, then I'm just going to throttle its page fault servicing. And I think this is feasible to implement even on edge devices because as they already analyzed in the paper, theoretically, there's at most 14 map IDs. And we are going to add one extra hardware counter per map ID. So there are at most 14 extra hardwares that we have to implement, which is not a big problem for our budget. There's also this coordination with memory schedulers idea that I had in mind. So here I do something like bank or channel aware placement, where I'd map, I would extend the mapping selector to somehow know in real time DRAM occupancy state and take some informed decisions based on this data. Basically, I'll put some PIM sensitive pages onto the underutilized channels and steer the SoC only pages onto other channels. And my last idea, which is the simplest one, would be bandwidth throttling. Basically, monitor processes at runtime. So we monitor their bandwidth utilization, which is again doable in current operating systems with tools like HTOP, for example, and also have a static threshold assigned at compile time. And if a process exceeds this threshold, then I'm just gonna throttle the amount of bytes per second it can get out of memory. That was my discussion section. This is also the paper if you're interested in reading more about it, the async DIM one. Thanks for your time. And if there are no other questions, we can close the presentation. Thank you for your attention. Yeah, thanks.